Okay, part A, calculate the spring constant for the wire. How are we going to calculate our spring constant? Rise over run, our gradient. So if we have a look at our graph on the previous slide, we can see that we've got, well, rise over run to the elastic limit. We've got a force of 40 newtons and an extension of 20 millimeters. So, can I do this? Sorry? I cannot do this. Not even, but you're on the right track. What do we always need distances in? Meters. Okay. So, we've got 20 millimeters, so it should be 20 times 10 to the negative 3. And so that will give us a spring constant of 2 times 10 to the 3 newtons per meter. Now, by the way, most spring constants will be in the thousands. Okay, you will have fairly high numbers for your spring constants. Okay, so yeah, simple as that. Just make sure that your force is in newtons and your extension is in meters when you're calculating these. Okay, calculate the strain potential energy that the wire can store before permanent deformation begins. So we want to work out how much energy we can store in our wire. Okay, again, this is just our area under the graph. Okay, if we've got a graph, we may as well use it. So, permanent deformation begins after the elastic limit, so we just need to work out the area under the graph up to the elastic limit. All right, so if we have a look at our graph, we have, so area under the graph is going to be equal to 1/2 times base times height. So what's our base? So 20 times 10 to the negative 3. Multiplied by 40 for our height. All right. Has anyone got a calculation for that? 0.004? 0.4? Yeah, so it's 400. Yeah, I like 0.4. Yep, I like 0.4. Okay. So, there we go. There's our energy that we can store. Now, as far as I know, we should be able to do this with our equation as well, our spring energy equation. So, let's try. Now, I haven't rehearsed this, so this could go horribly wrong, but let's try. So, from our previous slide, our spring energy is equal to 1/2 kx squared. So, unless I'm thinking about this incorrectly, this should give us the same answer, shouldn't it? Let's have a look. Equals 1/2 times 2000 times 20 times 10 to the negative 3 all squared.
Did we find the spring? Okay.
Spring constant is in part A. Yep. All right. So, let's see if this works. 0.2 squared 1000 equals 0.4. Look at that. Magic. So you can do it either way. You can use the equation, 1/2 k delta x squared, or you can use the area under the graph. Okay, either one's going to work. Okay, calculate the work done to break the wire. Now this one, we cannot use the equation. The equation only applies if our spring is obeying Hooke's law. And to break it, we need to move it into the plastic region where it doesn't obey Hooke's law. So the only way to work this out is to calculate the area under the graph. Now, if you have an area under the graph, like on that previous slide, if you've got a curvy line, what do? How do you work out the area under a graph with a curved line in it? You count the squares. No, don't worry about integration. That's way too hard. You count the squares. You estimate the number of squares that are underneath it. Okay? So a good rule of thumb is if more than half of the square is under the graph, you count it. If less than half is under the graph, you don't count it. And they should roughly even each other out. Okay? So if we count our area, or we count our number of graphs here, number of squares, I get 33. So area under the graph, I get 33 squares. Okay, have a count, make sure you agree with 33. Now, by the way, if you put 34 on an exam, you'd get full marks. Okay? It's because it's a little bit up to your opinion, but yeah, 34 would be fine. Or 32. Yeah. I'll go back and show you in a second. Okay? We'll just do this. For now, just take my word that I've got 33. Okay? So 33 squares. Now we need to work out what each square is worth. So each square is, well, let's have a look. Each square, yeah, is 10 newtons. Well, hang on, is it 5? Yeah, and 5 millimeters. So 5 times 10 to the negative 3. Okay? So the area of a single square is 10 times 5 times, so it's 5 times 10 to the negative 2. And then we have 33 of those. So we just multiply 5 times 10 to the negative 2 by 33. Yep, I like it. I get 1.65, but close enough. 1.65, what work done? Joules. Okay, so you can see that to reach our limit of proportionality, we only have to put in 0.4 of a joule. But to actually break it, we need a lot more energy than that, 1.65 joules. We need 4 times as much energy to break it. That's just a curiosity with springs. Okay,